Is my screen visible?
So far, so good. The moderator just joined, Il Yong Chung. Hi, Il Yong, morning. Yes, I can see your screen.
Right, perfect.
Il Yong is muted.
Oh, can you hear me, Helen?
Yes, good. Thank you.
Okay, yeah. How are you doing? Helen? Good to see you.
Good to see you. Yeah.
Yeah, good to see you. Yeah. Hey, Jitesh, how are you doing?
Hi, I'm good. What about you? How are you doing?
Good. I'm in Toronto right now, so it's 9 a.m. on a Sunday. Are you in Pune right now, or?
Yeah, I'm in Pune. It's 6:30 p.m. here on Sunday.
Yeah. Weather must be pretty nice too. So, and I think we have Dana on the call as well. Hey, Dana, how are you doing?
Hi.
Hey, yeah, good to see you. Okay, right. We are at 28 people. I guess I'll just kick it off, Helen, or should we just wait, or what do you think?
Yes, I can start the recording.
Okay, sounds good. Okay, yeah, all right. Well, everybody, thank you for joining another quantum computing meetup on a Sunday morning, this time at 9 a.m. Eastern time. I'm glad you all could make it. We have a very interesting talk series today, Quantums for Space, with the main speaker, Jitesh Lalwani. Got his Bachelor of Engineering at the Thadomal Shahini Engineering College, affiliated with the University of Mumbai. And he's coming from 15 years of experience in software dev and team management. He's now the founder and CEO of Artificial Brain, where he's leveraging quantum annealing to provide advanced optimization solutions better and faster than current classical algorithms. He's working with Simulation 2 in the energy and space domains. He currently has 2 papers on ResearchGate right now that you could check out. Quantum computing for Mars exploration, opportunities and challenges, and quantum computing for sustainable energy, optimizing wind farm layout for improved energy efficiency. Yeah, it's just an interesting read. I'll post the link to the ResearchGate down in the chat below. I think we're also joined with a guest speaker, Dana Lynette, as well. She's the former senior U.S. government official working with the U.S. Secretary of State, also working with the government affairs at Lockheed Martin, and is now currently the president and CEO of the Summit Group DC, working closely with organizations to solve problems and provide value, specifically in public sector facing companies in defense, space, and advanced technologies. So yeah, that's the intro that I had this morning, and without further ado, Jitesh and Dana.
Yeah, thank you for the kind introduction. Let me share my screen quickly. All right, let me know if my screen is visible.
Yep. Yeah, you're sharing your screen.
All right, perfect. So thank you for giving us the opportunity today to talk about our work and specifically quantum for space. My name is Jitesh Lalwani, and I'm the founder and CEO of Artificial Brain. Today, we are going to talk about how quantum technology can transform space, what are the applications of quantum in the space domain, and our recent work using quantum computing for solving some of the complex problems in the space domain. So little bit introduction about ourselves. So we are a quantum computing software company, and we develop quantum optimization software for 3 industries. So the first industry is space, the second is energy, and third is aviation. So we as a company are super focused on these 3 industries because we believe that these 3 industries are going through a transformation phase. When you talk about energy or utilities companies are transforming from fossil fuels to renewable sources. So the complexity for them has increased a lot. Same is with space and aviation. If we talk about aviation, the number of passengers traveling per year is increasing, and this has increased complexity for these three industries. And we believe that quantum can have a very big impact on these three industries, and we as a company can also contribute. And that's why we are focusing on these three industries. We have a global presence, and we are registered in the US, in Netherlands, and in India. And this is our team. So as I said, I'm founder and CEO. I have around 15 years of experience in the software industry. And before this startup, I was working with T Systems or Deutsche Telekom as a data science project manager, where I was leading a team of 60 plus engineers. Then we have Dana Linnet, who is our senior executive. She comes from federal. She has a lot of experience working with government, US government, and also with big organizations such as Lockheed Martin and a couple of startups. Then we have Amit Kumar, who is our senior quantum and AI engineer. And because we are into quantum domain, we need to do a lot of research. And that's why we have onboarded a couple of faculty members as research collaborators to our company. And we have also signed a couple of MOUs with universities such as the Christ University, Triple IT Delhi, and so on. Then we have Dr. Mandar Pandey and Dr. Anshul Saxena, who are working with us as research collaborators. Dr. Anshul has also recently published a book regarding finance, where he talks about what are the quantum applications in the finance domain. And the book is also available on Amazon and other marketplaces. Then we have a couple of advisors who are super experienced in the space domain, working with US federal government and so on. First one is Rafael, who himself is a space investor. He has his own venture fund, E2MC, where he invests in space startups. Then we have Bill. Bill has his own company, and 95% of his projects are with the federal government. Apart from that, he also has a lot of quantum experience, and he is personally working on projects related to quantum machine learning and quantum image processing. And then we have Craig Connell, who has around 30 years of experience in the software industry, and he's working as a CTO with one of the education platforms. These are our partners. We are part of Quantum Business Network from Europe. Then we have also signed an MOU with Boston Q Sci, and they are into quantum simulation. They are also one of the well-known quantum startups. Recently, we got a grant where we are going to write a white paper on wind farm optimization using quantum computing. And this grant was given by the Netherlands UK Innovation Network. Last year, we were also part of Quantum Startup Foundry from University of Maryland. And then we have signed a couple of MOUs. One is with the Christ University, and recently we did an MOU with Triple IT Delhi. And we have also found a system integrator, which is Akira. Akira has a lot of experience working with US federal government, and they will help us to sell our quantum software to US government and other US agencies. So now the $1 million or the $1 billion question is, why quantum for space? Why do we think that quantum can have a very big impact when we talk about space industry? First of all, space itself is highly complex. There are many use cases which require a lot of research. And that's why we believe that quantum can help to reduce the time that it requires to do research in the space domain. And there are many use cases which require dynamic decision making. We'll talk about some of the use cases shortly, but while we were doing our research, we figure out that this is where quantum can have a very big impact. Quantum can not only give better accuracy, but faster results. And this can matter to a lot of use cases in the space domain. Then space activities are very costly. right? And there are many activities which require millions of dollars of investment. And even if we can optimize 10% of all those operations, we can save a lot of money to these space agencies and space startups using quantum computing. And that can help to save a lot of money, not just to private sector, but also to the taxpayers around the globe. So now let's talk about in detail what are the use cases about quantum in the space domain. The first use case is in Earth observation area. So as we know that many government agencies, startup, and big organizations are uh, are launching a lot of satellites, especially in the LEO domain. So LEO is between 200 to 2000 kilometers above Earth. This is where we have about 6,000 satellites currently roaming in the LEO sector. So there are many applications when we talk about LEO. The first is fire monitoring, and this is a very big use case for governments around the globe, right? If there's a fire, uh, governments reach out to Earth observation satellite companies to monitor fire, and so that they can make informed decisions to stop fire in a short amount of time without doing a lot of damage. The second is water pollution, and as we know that water is very very important for us, but there's a lot of pollution happening thanks to industries, right? And this is where a lot of monitoring is being done to check how and when water is getting polluted. The third is crop monitoring and farm utilization. So this is the area where not just satellites but also drones are being used, so that the companies can make informed decisions on how to efficiently grow the crops. Now the first use case is related to the scheduling optimization of Earth observation satellite. If you see on the left hand side, there's an image and there's a satellite which is roaming above the Earth. This satellite needs to capture a lot of observation areas, or what we also call as targets. So these observation areas, which are marked as dots on the screen, right? They are scattered, and each of this observation area has different business value. For example, one observation area can fetch just $50 to the Earth observation company, whereas the other observation areas can fetch $100 or $150, $200 to Earth observation satellite companies. Then there are multiple constraints such as storage limit of satellite, energy limit of satellite, then ground station downlink time, then weather, cooling time of cameras, and so on. And on top of that, if you see on the right hand side, there can be multiple satellites in a constellation. So now the blue areas are the overlapping areas which are under these three satellites. So how these companies can make informed decisions on which observation areas needs to be captured, given that the combination of these observation areas should fetch maximum business value to Earth observation satellite companies, and also these observation areas should adhere to various constraints such as storage limit of satellite, weather, and so on. So this is an example of the use case. On the left hand side, these green dots are the observation areas which this satellite has to capture. And the algorithm has to make a decision which observation areas should be captured by the satellite in what order. And right hand side is the output of our algorithm. So red are the ones which are selected by our algorithm, and these red, the combination of these red dots or red observation area would have maximum business value, and that's the goal of our algorithm, to help identify this observation area or the combination of these observation areas which will fetch maximum business value to Earth observation satellite companies. All right. So our algorithm is also featured on DWare website. If you see on the right hand side bottom, this is where if you go to DWare website, our application can be found under featured applications. And because of this algorithm, we also won recently EU SPA competition. So this my EU space was a competition from European Union for Space Agency, and the idea was that uh, they asked for companies working in deep tech to submit their ideas under prototype stage, and we submitted our algorithm, and we also won the competition, and we got around 30,000 euros as a prize money, and now we have also become part of their startup network. The second use case is related to space debris, or what is also commonly referred as space junk. Because of many satellites that are being launched, the number of space debris is increasing day by day. And there is a syndrome known as Kessler syndrome, which was predicted by a NASA engineer that after some time, because of space junk or space debris, space would become unusable. And this is the fear of not just NASA, but of all the space agencies around the globe. And this is also a matter of security concern. If a country cannot launch satellite anymore, or if uh, the current satellites cannot capture images because of space debris, then the nations would not be able to capture images. And the second use case is regarding sustainability, or also known as space debris removal optimization. So there was already a use case which was executed in collaboration with UK Space Agency, Fujitsu, AWS, Astroscale, and University of Glasgow. And what they did is basically try to find out which space debris should be collected by spacecraft in what order. Given that every space debris again would have a different business value, different properties such as their orbit, their speed, size, and so on. So, how to make an informed decision to collect what or which space debris in what order? Given that a spacecraft cannot collect more space debris than the capacity of the spacecraft. This can be also considered as a knapsack problem. Okay, sorry for that. Just a minute. All right. So this is the result of the use case. On the left hand side, they said that the their digital annealer was 1,000 times faster than the current classical algorithm that is available and used by UK Space Agency. The optimization took a shorter time, plus it was able to save a lot of fuel. And also they were able to generate a lot of mission options for removing space debris in a short amount of time. On the right hand side, if you can see compute time, the compute time is around 240 minutes or 14,400 seconds. This was taken by a classical algorithm which is being used by them. Whereas the digital annealer just took 0.083 seconds. So you can see that even though digital annealer, which does not run on actual quantum computers, which is a replica of how quantum annealing works, it was still way faster than the current classical algorithms. Also, it was able to save fuel in the tune of 20 to 25%, and overall mission days that was required to collect the same amount of space debris was also reduced by 25%. So this use case is available on YouTube. Anybody can go and watch on YouTube how they were able to leverage digital annealing based on quantum annealing for this particular use case. The third use case is satellite placement optimization. And the goal is to figure out how to place satellites such that they can cover maximum area at a minimum cost. This use case is also an NP-hard problem and is very, very difficult to solve using the current classical algorithms that we have. A similar use case that we executed in the past was location optimization of EV chargers, where the goal was to find the best locations for placing EV chargers using quantum computing. Then the second goal of this use case is to place satellite in such an order so that they can avoid collisions with the existing satellites or the current space debris. The fourth use case is in deep space network. To communicate with satellites or objects in deep space, there are three antennas which are placed on Earth. One antenna is in the United States, the other is in Spain, and the third one is in Australia. And because these antennas are limited, there's a lot of requests which are going to these companies or agencies to leverage these antennas. Then the goal is to how to optimize or create an optimal schedule for this deep space networks. So this is where Microsoft Azure did a project with NASA, and they were able to reduce the time that it requires to create an optimal scheduling from 2 hours to just 16 minutes, right? And then after doing further modification or optimization, they were able to reduce the time from 16 minutes to just 2 minutes. So this use case is also is available on internet, where Microsoft is talking about why quantum was used for this particular use case, what was the advantage, and how they leverage quantum for this particular use case. And the next use case is a very interesting use case where we have also published a paper. So there are many problems when we talk about Mars exploration or terraforming Mars. So the first problem is regarding how to survive on Mars environment. So there's a lot of optimization that would be required in terms of trajectory optimization of spacecraft, the limited resources available on Mars, obviously mission planning, scheduling, and so on. And this is where we believe that quantum can play a big role. There's a lot of optimization that is required, and quantum can do that. Then, apart from optimization, there's also requirement of lot of simulation. We have to develop novel materials for battery and fuel, because the materials or the environment on Mars is different than Earth. So the same materials will not be able to work on Mars. So how do we find an optimal material? And this is where quantum simulation can be very useful. Then secure communications. So this is already being done by a couple of companies where they are already leveraging quantum communication or security. Sorry. Okay. The fourth one is quantum machine learning. Because there's a lot of data being generated, it is becoming impossible for the current classical machine learning to do analysis, especially in a short amount of time. And this is where quantum machine learning can come into picture. And there are already papers which are published that demonstrate that quantum machine learning can be faster, and it also requires less amount of data to give the same accuracy provided by the current machine learning algorithms. Apart from this, there are other notable quantum use cases. The first is efficient design of spacecraft and rockets using quantum simulation. The second one is quantum ghost imaging. And the idea is that it is very, very hard to detect space debris which are very small in size, less than 1 centimeter. And there are millions of space debris that are less than 1 centimeter, and it's very hard to detect those kind of space debris. And this is where a technique which is quantum ghost imaging can be used. Of course, it is very difficult in practice to leverage quantum ghost imaging, but at least in theory, this can be used. Then again, as I mentioned, quantum machine learning. This can be used for collision avoidance and detection. And the fourth is secure quantum communication between satellites or satellites to ground station. And we have already done some work around those use cases, and the papers are already available on ResearchGate. All right, so before I move to example, are there any questions from audience, and I would be happy to answer them.
Yeah, there is always questions. And very, very exciting slew of futuristic projects, very impressive. And the question is, on your last slide, you say I can avoid collisions with QML and detect collisions.
Yes.
So can I relate this to the problem of driverless car on our simple road, not in space?
I'm sorry, I could not understand your question. Can you please repeat the last part?
I think, Jitesh, he's asking if, this is Dana here, the co-presenter, if, it's great we can detect and avoid collisions in space, but here terrestrially on Earth, can this be used with cars to avoid and detect collision or detect and avoid collisions in our automobiles?
Yeah, of course, it can be used, right? Because we are concentrating more on space. These are the use cases that we have listed from a space perspective. But some of the use cases can also be used for, as you said, for collision avoidance between vehicles, detecting collision, and so on. In fact, as I mentioned on this particular slide, here we just like satellite placement optimization, we have done a similar use case for EV charging placement optimization, where the goal was to find the best locations for placing EV chargers such that those EV chargers can cover maximum population at a minimum cost, right? So yes, there are similar use cases which can be done on Earth, right? And we will be happy to also contribute there, right? But yeah, it is very much possible.
And Jitesh, there was one question in the chat asking if you could post the link at some point to the book that you referenced that was available on Amazon. We had a few people asking for that.
Yeah, I will do that. That is from Dr. Anshul Saxena. It's a very good book related to finance, and I will do that.
Great.
Lewis just dropped a question in the chat as well. She's asking what methodologies have resulted from this work to effectively remove the space debris or space junk.
Okay, let me go to that particular use case. Okay, so all right. So as I mentioned, the problem is more like a knapsack problem, right? So the idea is that.
Sorry, that means national security. We can't use jargon. Jitesh.
Yeah.
National security.
Yeah. So so the idea is that there would be a spacecraft that will go up, collect space debris, and bring it back to Earth atmosphere, where the space junk or debris will burn on its own, right? Now, there was a recent news that the spacecraft who went to collect space debris was itself being hit by a space debris, right? So now, how would you avoid collision not with the satellites and spacecraft, but also with vehicles or spacecraft that are going up and collecting space debris? So this is the use case, which is also known as space debris removal optimization, where the goal is to collect space debris efficiently, and also to make sure that the spacecraft itself won't collide with the space debris. So this would also have a very big impact on national security, as I mentioned. If the current satellites are being hit by space debris, or there's a risk that they are going to be hit by space debris, they won't be able to capture images, right? So what governments around the world are doing, they are putting a lot of money. They are coming up with novel methods how this problem can be solved. And this is where we believe that quantum can be used.
And Jitesh, this is Dana again. So there are a number of companies that it's not just a government problem, it's commercial as well. Commercial satellites make up the majority of what's in space. So that's an issue for them as well, because they're making private investment and have to ensure that investment's viability in space with all this junk. But Jitesh is right, the government's become responsible legally for the assets that are coming from their territories nationally, whether they're commercial or space. The other issue is the question was what was being done. There are a lot of AI and AI machine learning startups out there that are trying to address the issue. They've been very good in terms of some experimentation on repositioning satellites. So getting the satellite to move, assuming the satellite has the energy and power to move itself, to position itself to avoid getting hit kind of on a constant basis. But what we haven't solved is the overall, and there are a lot of other startup companies that are looking at space debris and how to apply AI and stuff toward that. But the problem is that, again, as the data is borne out by this current experiment, plus all the experiments we've been running on our own artificial brain software on hardware, quantum hardware, is that quantum is able to make these calculations almost instantaneously to make that actual real-time decision-making in orders of magnitude that even the best optimizers for AI are not. And that's where we're seeing some, at least early promise of quantum advantage or some sort of quantum advantage in these calculations now. And that's why, you can layer in AI and you can use AI in pre and post processing, but you really need the quantum, computing to really get us over the hump and really get us to solve these problems and solve them faster, because we don't have the kind of time that the current AI and even in some of the best startups are able to provide. So I hope that helps clarify.
So Jitesh, there's 3 other questions. Did you want to answer them now, or did you want to answer them after the presentation?
Yeah, we can take 1 or 2 now, and then
Okay.
maybe later. Yeah.
All right, sounds good. Yeah, so somebody asked on YouTube, it was Martin, will quantum computing be easier in space because it is so cold?
Yeah, so that's a very good question. Yeah, so when we say quantum for space, we don't necessarily mean that we have to run quantum computing in space, right? That's not the idea here. The idea is that most of the calculations or optimization is still done on ground, right? On Earth. And this is where you can leverage quantum computers available on Earth using either IBM or D-Wave. And you can do a lot of calculations and can pass on those calculations to satellite or spacecraft. The other thing is there is also something called as quantum inspired algorithms, just like digital annealing. Those are the algorithms that don't run on actual quantum computers, but they run on classical computers or on satellites. The only difference is that those algorithms are inspired by quantum. So there is also a way where you can run your quantum inspired algorithms on satellite or spacecraft. And this is also known as edge computing.
So, let me just add on to Jitesh's answer, because it's a really good question, right? The photonic hardware, the gate photonic hardware is different than the quantum annealing hardware. So you have to differentiate between the hardware, and but I would say that it's an interesting question because quantum hardware does have to be kept cold. So I get where it's coming from. Who knows if in the future quantum computers will be able to operate in the cold area of space in their own way. I'm sure somebody's working on that. As Jitesh said, our company's a software company, so we're able to run the calculations, the mission planning, the simulations, and also the relays coming from space pretty instantaneously with software. But what you're talking about is a hardware problem. So they're kind of two different, as Jitesh said, two different parts of quantum, I guess the quantum technology ecosystem. But we have been approached by another company who does want to run our software, our quantum-like software on some more classical hardware in space, just to prove that out. But yeah, I would love to see one day where we can run our quantum algorithm from space on hardware in space, but that's not quite there yet. Jitesh, do you want to finish out the thing and then we can take more questions at the end?
Yeah, I think I will move on with an example, and then we can complete the rest of the slides, and then we'll answer. All right. Cool. So let me go to an example. Okay. So this is an example of our algorithm, which is scheduling optimization of Earth observation satellites. All right. First of all, why this is a complicated problem, right? So if you see on my screen, let's say the total number of targets that need to be captured is just 10. And the maximum number of targets that can be captured by a satellite is 4 due to, let's say, constraints such as energy constraint or storage constraint, weather, and so on. So the number of combination which is possible only with 10 targets is 210. Now, when you increase the target to 1000 and 40 targets can be captured, so this is the number of combinations that are possible. 5.559 into 10 raised to 71. Right? This is just only with 1000 targets that needs to be captured. And satellite companies get a lot of requests in the tune of thousands to millions to capture observation areas. Now just imagine how big is the number, how many combinations are possible. That could be probably in billions, if not trillions. So the decision has to be made in a short amount of time, because inputs are always coming and the satellite is always orbiting. So if, again, as an example, if there are 10,000 targets that need to be captured, and the maximum number of targets that can be captured because of constraint is 400, then these are the number of combination that is currently possible. So I will now show an example of our algorithm. So this is the input that can be given by Earth observation satellite companies to our algorithm. The first is the target ID. So each observation area or target can be identified by an ID such as T1, T2, T14, and so on. And each of these targets have different priorities. So these priorities are either based on the business value or how important the observation area is. For example, if there's a fire burning in a forest, then obviously that observation area has the highest priority. Or if an observation area has highest business value, then to the priority of that target is highest. So user can also give a list of priorities to our algorithm, followed by size of targets, energy of targets, and so on. So this input can be given to our algorithm. This is an example of API. So we can also make our algorithm available as an API, so that Earth observation companies don't have to install anything. The developers don't have to learn quantum. They can just integrate quantum solution into their existing existing architecture using an API. So when this input is given to our algorithm, output would be something like follows. So it will return a list of targets that can be captured by one satellite or n number of satellites. So for this input, we have given three satellites. So our algorithm is flexible. It can work with one satellite or n number of satellites. So this is a list of targets that the quantum algorithm has written. Currently, this is a quantum annealing algorithm that runs on D-Wave hardware, but this can run on any quantum annealing hardware provider. So the second parameter written by our algorithm is very, very important. So this is the total priority of all the individual targets or observation areas. So this is currently 431. Again, there can be millions of combinations and there can be different priorities or business values. But the goal of our algorithm is to return the combination of these targets, which will return highest business value or highest priority value. And this is the execution time that it took for our algorithm. This also include latency, cloud latency time. So when we run our algorithm, it runs on D-Wave hardware provider, so we have to run it on cloud. Apart from that, it also will also tell us whether it was able to satisfy all constraint or not. So in our research, we have run it for 12,000 targets, which is a very big number, and there are billions of combinations possible. So for even 12,000 targets, it was able to satisfy all the constraints. I will also talk about benchmarking shortly after this screen, but this is what our algorithm will return, whether it was able to satisfy constraint or not. And apart from that, it will also divide the target as per satellite. For example, it will tell us if there are overlapping targets, which satellite should capture which target. So our algorithm will also take care of not only returning the observation areas having maximum business value in a short amount of time, but it will tell us which satellite should be responsible for capturing which observation area in what order. So this is a benchmarking result. So what we did is basically we compared our quantum algorithm with two classical algorithms. The first one was simulated annealing, which is just like quantum annealing, but it runs on classical computers. The second is Garobi optimizer. And Garobi optimizer is one of the best classical optimizers available. And these are the results of our benchmarking. So we found out that our algorithm was able to return the highest business value, or the combination of these targets were having the highest priority. Quantum was able to return a mean of 50,000, whereas simulated annealing was able to return 17,000 on an average. And this was done for 1,000 rows. So each row had a random number of targets, and it was, as I mentioned, the number of targets were generated randomly anywhere from 5, 10, 500 to 1,000. And the Garobi optimizer, which is the best classical optimizer available, it was able to return a mean of 35,000. The second parameter was the execution speed. And sorry, and quantum was able to return results in 23 seconds, including the cloud latency time, whereas simulated annealing was the faster among them. It was able to return results in just 2 seconds. And Garobi optimizer was able to return a result in 39 seconds. But as I mentioned, even though simulated annealing was faster, it was the one which performed poorly when we talk about accuracy. So it gave results faster, but they were not accurate. And the third, which was very, very important for us. So we tried to also figure out which algorithm was able to satisfy all the constraint when the input size was increasing. And we found out that quantum was able to satisfy all the constraint for all of the data. Whereas simulated annealing again performed poorly. So this graph that we are showing now is for around approximately 85 rows, and each one having around 1000 targets. But this graph would depend on the number of input given. So every input would have different graphs. But this is graph for 1000 targets. And simulated annealing was not able to perform or not able to satisfy all the constraints for all of the data. For example, the constraint were satellite storage, energy storage, weather, downlink window time, cooling time of cameras, and so on. So it was able to return results without satisfying all the constraints. And the third one, Garobi optimizer, it was able to satisfy constraint for some of the data, but not all of the data. So for 20 to 25% of the data, it was not able to satisfy all the constraints. And for some of the data, we have to manually stop the Garobi optimizer because it went into a loop. So it was not able to find global optima, and it got stuck in local optima. And that's the reason we have to manually stop our Garobi optimizer. So before moving to the next slides, which talk about business, right? Are there any questions about this example? And just for your information, we have also published a paper where we have demonstrated all of the results that I talked just now.
Yeah, there's a lot of questions, but I guess I could just bring up the question specific to the code. Yeah, there's a lot of questions, but yeah, somebody was, well, I guess in relation to what you just shared, someone was asking if you could share the code. Is that something you can do or no?
No, we can't. Sorry.
No.
I mean,
Emphatically no.
That's what I thought. Yeah, and then somebody else asked, Kino asked, what was your error rate in this specific example?
So in general, if you are talking about number of shots, right? So it was 1000. The thing is that we did not did any error correction, right? Because when you're working on quantum annealing, you don't do error correction. That is done by D-Wave itself. So we did not do any error correction for this particular use case. But on the other use cases where we are working on quantum machine learning that we need to run gate-based model, there we do a lot of error correction, but not for this particular use case.
And Jitesh, is that a factor of annealing versus gate hardware, or is that a factor of the software? Because I thought it was more hardware related, but
I mean, the architecture is different. When we talk about quantum annealing, it's it's a specialized form of quantum computing, right? They are not universal quantum computers. So the problems are different between these two architectures, and also the use cases are different. For example, if we want to work on optimization use cases, this is where quantum annealing can deliver the results now. And that's why we are focusing a lot of use cases that are running on quantum annealing versus on gate based.
Cool. Yeah, I think this is related to your example. Someone was asking, are you applying simplex method or other linear programming to solve this large data under all large constraints?
So I think Amit would have been a better person from my team to answer that. I don't want to give wrong answers. But
yeah, we can take that back to Ahmed and get the person the answer.
Yeah.
Okay.
He's our lead engineer on that helped develop the algorithm with us. So
Well, I think that was all the questions that was related to the specific example.
Okay.
There's a lot of yeah, I think you should just go ahead with the presentation and we can just ask the rest of the questions at the end.
Perfect. So I think this is where Dana will come into picture. Dana, over to you.
Hi, thanks. Yeah, so just real quickly, I know we're coming up on some time here, but so we are looking at applying our quantum annealing algorithms to really transform markets. So if you look at space, which is the topic of our interest today, we're looking at this almost $500 billion space market right now, headed to over $1 trillion in the next less than 10 years. So this is a really fast-moving, quickly transforming market. So we want to make sure we're injecting some quantum advantage to help maximize that capital return, but also to get where we're going faster. If we take the subset of that, the Earth observation market alone is just under 6 billion. It's going to go up to, some people say 11, some people say 12 by 2031, again, in very short order. And now we're seeing also government looking to commercial satellites to buy capabilities. So it's not just the government putting up its own satellite and commercial companies doing things there. It's very blended, and the market is set to project to a very high market cap value. And so with a lot of interest, a lot of blended interest. So again, we want to maximize the capital ROI. If I'm an investor, and I am an investor, but I want to see my return faster, and I don't want to see spillage of anything, waste of any money, being used on anything that isn't going to get us there faster. We can also create those resource efficiencies. Again, if let's say you're Maxar satellite company, or you're one of these other commercial satellite companies, and you've got a ton of commercial clients and you've got some government clients, how do you know what to look at and when, given your lower Earth orbit positioning? You might have 9 minutes over a certain area to cover. How do you know which images to capture, what their values are, where they're going, and how to order and sequence them? You just can't do it. You just can't do it with AI right now to the level that you can with quantum, and you can't do it fast enough. So you want to create those resource efficiencies. Also, if we're going to send up so many satellites with so many constellations, if I can send up 5 satellites in a launch and cover 100 things using quantum, why would I send up 20 satellites to cover 5 things? So you see, there are resource efficiencies that also creates less space junk and so on. And again, better customer experience. Right now, it's, customers worldwide are kind of not happy, whether it's aviation or whether it's with the battery life on their car and when they can get the next charge and so on. But for space, we want to create a better customer experience with in terms of those customers that need that imagery, or need to make that decision making, or need to save lives, or need to find the human traffickers from space or the arms traffickers from space. There's a lot of on the customer experience side. Also, when you start looking at the communications that are going to come from space to benefit us here on Earth, the commercial benefits are important, but ask any commercial company, it's customers. So we don't want to lose sight of that. In the end, artificial brain and others like us will be serving that customer. Right now, there's a perception, if we move to the next point, there's a perception that quantum somehow is this futuristic thing. It can only be, we need to wait like 5 or 10 years till it matures to perfection. And that's never been the case with any technological rollout. I mean, who remembers when you had this gigantic clunky, phone, attached to your ear, and now we have these little things. In terms of the algorithms that we have, we can thanks to what Jitesh is saying, that classical gate quantum photonic hardware is different than quantum annealing hardware. And so our annealing algorithms and on annealing hardware can be leveraged right now for these optimizations that can be Gurubi optimizations and AI optimizations, and they can be used with AI. So it's not an either or choice. So the point is not an either or choice. And we don't have to wait for the future to seize on the technology that we have now. The more we seize on it now, obviously, the more we can continue to better it for the future as well. Society is we are leaving money and progress on the table if we're just waiting around for the perfect gate hardware to emerge before we accept the available quantum annealing that we have now. There is, I think, some perceptions in the academic community that somehow like quantum annealing isn't real quantum, and that's just rubbish. Quantum annealing and quantum algorithms are quantum. They're quantum technology, and it's not, again, even within the quantum sector, it's not an either or. We have lots of availability right now, and we need to be seizing on that availability. Otherwise, we're going to be wasting our capital investments, wasting our resources, our human resources, and we don't have a lot of these things. These are scarce. Parameters. So, we can break through that scarcity, reduce that scarcity, and we can get where we need to go on all of this, on space exploration, the existential threats of space junk. On Earth, we can do it with net zero transformation or aviation and so on. So there are plenty of use cases. These are just the ones we're working on specifically. We're not ruling any others out, but we're focusing our scarce energy on our expertise, which is in the space domain. So thank you for that slide. As a company, we offer highly experienced and focused customer-focused teams. Again, bring us your challenges. We want to help you solve these challenges. If industry and industry associations want to crowdsource certain things among their members and bring those challenges to us, we will work with you to solve them. Again, quantum annealing is a ready technology. Unlike AI, I worked in the AI business. You have to spend a considerable amount of time training your large language models or training your AI models. That's not the case with quantum. You don't need to train the model to get it to work efficiently. What we do is we give it the parameters that are unique to your problems. Again, because when you're trying to solve for, let's say 1,000 different types of complexity at once, yes, you have to give the model that data for it to be able to solve that NP hard problem. But you don't have to spend months and months, ingesting past data to train a model to do a thing. That's not how quantum works. So I hope that helps dispel a myth. The other thing that artificial brain is doing, there's a reason we're partnering with academic and R&D to help our commercial product evolve. But we really do want to have that circulation of academic and rigor and testing in our commercial R&D, as alongside working with our commercial customers and government customers to help them solve their problems. The more we work together to loop, to OODA loop or loop our academic R&D and our commercial R&D together, the faster that we will develop these out of the box and off the shelf use cases. So, the last thing I'll say is that artificial brain is looking to work with, we have great relationships with so many government and commercial and academic entities, but we're looking to work with folks in the quantum ecosystem, or even if you're not in the quantum ecosystem and you want to use quantum, but we want to have a lasting and profitable business relationship with you. We're not interested in people who just want to come in and, here, I want to make some money and get out, or, I don't really believe in quantum, but I'll want to do some things and play around and waste some time, doing this. We're not really interested in that. We want to have a lasting, profitable business relationship with these transformative industries and people who care about that transformation and care about our ability as humans to evolve. And quantum will evolve. You're hearing it now, maybe not for the first time, but you're hearing it for the next time, and you'll hear it the next time and the next time. But the quantum market is really fast evolving, and we have seen people kind of be asleep at the wheel of where things were 5 and 10 years ago and where things are now. They're quite astounded at how the research and how the data have proven quantum computing have proven that out. So, we're in this for the long haul. So I'll stop right there and we can take some more questions.
Cool. Yeah, there's a lot of questions in chat. So I'm gonna start with Caetano Pang's question. In the speed comparison, how many qubits and cores were used in the quantum and classical computations?
Yeah, so all of the data has been published in the technical paper, right? All the questions I think would be answered there. So again, with quantum annealing, you don't have to actually worry about the number of qubits, right? So the number of qubits is different than you talk about gate-based model, right? So when you talk about IBM, we are talking about 400 qubits, now 1000 qubits and so on, right? Whereas when you talk about quantum annealing, they already have 5000 qubits, right? So the idea behind the number of qubits is different when you talk about quantum annealing versus gate-based model, right? But all the details, what machine did we use, which was the classical optimizer that we used, how big was the data, what was the speed and such like, everything is mentioned in the technical paper. So I will be posting the link of the paper now in the chat, right? And all these answers would be found in that paper.
And if people want to follow up with us after they've read the paper, Jitesh and our technical team, our engineering team would be happy to engage.
Great. So another question from Lewis. Wouldn't the collection of debris have to be done as an international collaboration?
No, because not necessarily. I mean, you could, but the way that the international law is written now is that whose ever space junk it is, they're responsible for it. So if the Chinese put up a satellite, whether it's commercial or government, and they descend that satellite in a dangerous way that hurts or kills people, they're actually legally culpable for that. So you're responsible for your space junk and your space debris as a country because of the way that these very antiquated and outdated laws are written, but these international agreements are still in force and nothing's been rewritten. And I don't think that I won't speak for the United States, but I will speak from the experience of having negotiated some of these types of agreements in the past, that you still want countries to assume responsibility for their assets in some way. So the space junk issue, it becomes complicated because if you're in space and something's traveling at 30, 40,000 miles an hour, even like something big can hit something and you now have 3,000 pieces of debris out of that one thing. And then other things hit that and now you have like 100,000 pieces of debris. So there's literally like millions of pieces of debris at every single kind of level, whether it's big, small, or even barely visible. There's a lot of space junk up there. A lot of companies, my former company, Lockheed Martin, has space fence for this reason, to protect satellites. But at some point, you have to get rid of this junk. And I really applaud those. I've met some of these space startups that are working on how to scoop it up and get it out of there and even repurpose it or recycle it, even recycling it in space in a cislunar or other in a LEO environment. It doesn't necessarily even have to come back to Earth. So there's a lot of really cool research going on in the space debris, but our algorithms can help them get there faster, solve the problem faster, target the right debris in the right area, and also to, as Jitesh said, help them to not get hit by this millions of pieces of space junk that they're navigating amongst.
Great. Moving on to the next question. Abhishek asked, how many qubits did you use to run your algorithm, and which quantum computer vendor did you go with? So obviously it's D-Wave, but how many qubits? they're asking.
So again, we use a quantum annealing algorithm, which we tested on D-Wave, but it can be executed on any quantum annealing provider, right? So the number of qubits that is available as of now is around 5,000 qubits. We again can't go into details because a lot of things we did it while doing research, right? So a lot of things are is our secret sauce. So we can't go into detail, but the number of qubits available as of now is 5,000. And obviously, it also depends upon the input size, right? When you are giving 1,000 targets versus you are giving 12,000 targets, the number of qubits will be different. So we tested until 12,000 targets, which is a very big number. And we were able to successfully get results on D-Wave, but not on Garobi or not on simultaneous annealing as of now.
Right. So the D-Wave is the one that we used, and D-Wave will tell you that whatever's publicly available, it could be more or less, or not less, but maybe more. We don't know. But yeah, you'd have to ask them.
Great. Joe Reddix, given the massive data being provided by edge technologies and autonomous devices, do you see integration with quantum space and devices like drones?
Yeah, I think this is where quantum machine learning will come into picture, right? To do a lot of data analysis. This is where we believe that quantum machine learning can be helpful, and we are already doing a research on that. In fact, one of the government agencies, they have reached out to us if we can help them on solving this space debris problem, and we might work with them for the next 5 years. But I can't disclose much details as of now.
Yeah, to be disclosed later.
Right. As Mita asked, can we integrate any LLM-based ML model APIs to inference any quantum ML or optimization problem use case results?
Sorry, I did not understand the question.
Yeah, I don't know if Mita's in the chat right now. If they want to.
Okay, I will check it.
So are they asking about being able to integrate quantum into a large language model type algorithm?
Yeah, they're just asking if they can integrate ML model APIs to.
Yeah, we are not sure about that, but if we talk about generative AI, there is a field which is quantum generative AI, right? Where companies are doing research how quantum can be useful for generative AI. And what we are doing as a company is that we are also making our quantum software available as an API so that they can be integrated in existing solutions, right? So we are trying to make easier for companies to leverage quantum without learning quantum.
But I would say to the questioner, if you want to go and find some research funding to solve that problem, we could probably get the right engineer to test that out. So we're open to working with you to test it out.
Right. Yeah, so moving on, Nick had a question in the chat as well. Regarding extrapolating funding, are you worried that a disproportionate amount of funding has been allocated to buy the startup of the US Space Force, assuming similar or constantly growing funding might be a mistake?
I can take that one. Space Force, as the US Space Force, doesn't have enough funding, but they have been some of the most innovative in government contracting, to the point where other government military contracting and acquisition officials are looking at how Space Force is doing things. So I don't think they're taking up too much space. They don't have enough space or enough investment. I think they're maximizing the use of the startups that are out there and helping to fund existential research and use cases that are solving real world problems that we need to solve. They're working with commercial companies, startups. So no, I think it's, in fact, if we didn't have the Space Force injecting taxpayer money into some of these really incredible space and other startups, these really important startups would not be funded. They wouldn't have the investor confidence and backing that they have now. And in fact, in some of the most cutting edge research, it's the government that's keeping some of these startups afloat in really good ways so that the market can catch up. And quantum in a way is part of that. So governments, not just here, but in Europe, are doing a huge amount of quantum research because the commercial market and the investors' mindset can't wrap their mind around quantum yet, and some of these other technologies yet. So yeah, I'm a big fan. The amount of taxpayer money that is going into this stuff is a tiny, it's a rounding error at best in terms of the overall budget. So it's not anything that's consequential for the government budgets, but super consequential in terms of our human race's ability to get these technologies developed that are going to benefit everyone. It's not just going to benefit the governments, it's going to benefit actual taxpayers and actual humans here on Earth. I hope that answers the question. Yeah, I like there was something in the chat, more funding should go to NASA. So NASA, yes, civilian space, and NASA does a lot of cooperative agreements, international agreements with governments from India to UAE and Australia and Ecuador, or I think it's maybe Peru. So yeah, I mean, NASA is working with, countries in Africa, pretty much everywhere on the globe. So on the civilian space side, yeah, we would love to see more funding into NASA. Yeah, and DARPA is also putting money in. By the startup of the U.S. Space Force, yeah, I mean, U.S. Space Force is essential, as a war fighting domain. So very important that money went into starting that up. So yeah, I hope that answers the question.
Great. So moving on, Deb had a question. Are you providing data processing support for academic purpose or business purposes? If yes, please share a link from where we could apply.
No, we are not doing that. We are not into data processing business, right? So, I mean, we can help with that using quantum machine learning, right? But we are not into data processing as of now.
Great. And they're just asking for the link to the book again, Jitesh.
Yeah, I already posted now.
Okay.
Yeah.
There it is. Yep.
Okay, sounds good. Yeah, just another question in the chat about that. Oh yeah, I just see it now. Okay. Yeah, and then Jordan just asked just recently, when you say use API, do you mean API to call your hardware/data center to run the software, or is this an API call to any annealing hardware to run your software?
Any annealing hardware, right? So it depends upon customer. If they are already leveraging D-Wave, they can provide us API key to D-Wave, and we can consume that in our API. So the idea is that our quantum software is made available as an API, so that consumers or customers don't have to worry about which hardware we are using in the backend, right? But if they want to use a specific hardware, we can also do that. They just have to share the API key or access to that particular hardware, and our software will be able to run on that particular hardware.
Great. Yeah, so that's all the questions that we had in the chat. That was a lot of questions. Thank you for answering those questions. I guess I'll just do one more call out for any other questions. Feel free to drop in the chat. Just gonna wait like 3 seconds. Yeah, so we are available on LinkedIn. Dana and I are very active over there. So if someone wants to collaborate with us, if they have any further questions, they can reach out to us on LinkedIn. We also have our company profile page on LinkedIn. They can follow there, where we keep on posting all the updates, all the work that we are doing, right? But again, so thank you for giving us the opportunity today to talk about our work, and we will be happy to also connect after this meeting if somebody have a specific questions or they want any project where they want to collaborate with us. Yeah, I will definitely be connecting with you guys on LinkedIn. Thanks for coming once again, Jitesh and Dana. It was a very insightful presentation. It was very refreshing to hear about, actual use cases using quantum computing. Just for, like there's just been a lot of academic talks in this group. So, really seeing a real use case where quantum computing is surpassing classical computing is exciting. And I think, it's instead of like it's becoming a more of a realistic future for quantum computing and real business use cases. Really excited to see where you guys end up. Got a really good niche there. And I'm sure that industry will grow, like what Dana said, $1 trillion. I think it's a good spot. I think you guys are a pretty great spot. So I hope you guys do pretty well. And just, in terms of the meetup stuff, thanks everyone for coming. Just quick reminder that there is another meetup next Sunday at 2 p.m. Eastern time. It'll be GDS Factory and open source Python flow for circuit design. Hope to see everybody there. And that's on my end. Helen, did you have anything you wanted to add before we close it off?
Thank you for all the participation.
Okay. Yeah. Thank you everybody for participation. Thank you, Dana and Jitesh, for joining this call on a Sunday morning. I think it's afternoon for you, Jitesh, right now, evening.
Evening,
Yeah, it was great talk, great chat. A lot of people were just saying great session, very interesting topics. So I think, it was pretty great. And enjoy the rest of your Sundays.
Yeah, thanks for having us. And we know you have a lot of things you could be doing on a Sunday morning. So we're pretty grateful that you spent it with us nerding out here on quantum space use cases. So thanks.
Yeah, no, it's great. Yeah, it's great
Thanks
chat.
for having us.
Okay.
Thank
Well,
you.
have a great rest of the day, everybody.
Bye.
Yeah, thank you. Bye. Take care.